Yeah, so RMR is what we need to get to. And the reason we need to get to it, I'll come to in a moment. But first of all, how soon do I think we're going to get there? I think we've got a 50-50 chance of getting there in about 3 years, just so long as I get that money in the door to do the experiments. I think we're talking about, maybe three more of these studies done bigger, probably done in parallel, so that we can get them all done in 3 years, right? Um, uh, all right, so then what? Well, this is the thing. I believe that things are going to move extremely fast from that point. The first thing that's going to happen is, well, experts are going to come out and start saying, yeah, you know what, we're in a new world.
Our guest today is Dr. Aubrey de Grey, internationally recognized as the visionary biomedical gerontologist who devised the strategies for engineered negligible senescence, a comprehensive set of methods to rejuvenate the human body. He has co-founded multiple influential organizations, including Methuselah Foundation, Sense Research Foundation, and most recently the LEV Foundation. Aubrey, welcome to the Levity podcast.
Well, thank you for having me.
Are you interested in football, by the way?
Only recreationally, only a little bit. I've never actually been to a live football match.
But you're familiar with Jürgen Klopp?
Oh, yes, very much so, yes.
Yeah.
When I grew up, that was the era in which Liverpool were the dominant team in British football. And of course, since they have become dominant again, I'm quite happy about that. And Jürgen Klopp has a lot to do with that, of course.
And the reason I bring it up is because he turned Liverpool around as a club, and there was this saying that he was going to turn doubters into believers. And I think that you could say that about you as well, that you have turned doubters into believers.
Well, I guess one could say that, but that's not really how I see it. I see more a case of I've turned people who are despairing into people who are not despairing. So people who already have no doubts that aging is a bad thing and it would be rather good if we could fix it, into people who no longer believe that actually we can't fix it, and now believe that we have a chance. That's what I've tried to do, really. I've tried to inspire people to aim high.
Yeah, you've certainly inspired a lot of people. Every time you talk about where did your interest in longevity start, it's almost impossible to get an answer that doesn't start with Aubrey de Grey.
Yeah, I'm very proud of that. I mean, honestly, I'm just as proud of that as I am of the scientific contributions I've made.
Yeah, and let's talk a little bit about the scientific contributions then. Maybe we should start with the Longevity Escape Velocity Foundation's latest update on the Robust Mouse Rejuvenation study that came in December, I think, December 2024. But to do that, maybe we need some context here. So could you briefly tell us what the LEV Foundation is and what you're hoping to achieve?
Yeah, you're right that I think I need to give some context. So I think I need to go back in time a little bit first. So I've made a variety of scientific contributions, but certainly the one that I'm most known for and that I would regard as the most significant one is the realization about 25 years ago now that repairing aging, in other words, taking people back to a younger biological age, is going to be easier to achieve medically than slowing aging down. This is something that was very counterintuitive when I first put it forward. In fact, it took quite a few years for almost anybody to even understand what I was saying. But of course, it has now become very much a mainstream way of thinking about the whole thing. And the thing is that if you're trying to do this, repairing the damage that the body does to itself throughout life as a consequence of its normal operation, and that eventually kills us, then, simplistically, it's just preventative maintenance. But you can't do it unless you drill down to what it actually consists of physically. So any machine, even a simple man-made machine, will do itself various different types of damage. Like, a car will rust, and it will also accumulate, like contamination in the oil, things like that. Um, and the ways in which we do this preventative maintenance are specific to different types of damage. So, when you take a car in to be serviced, the mechanic does lots of things. Now, of course, with an astronomically more complicated machine like the human body, you have a lot more types of damage that accumulate. And so that means doing a lot of different things to the same individual at the same time. And that's just as true if we're working in the laboratory in model organisms like mice, which is, of course, where discoveries tend to get made in the first place. So that means we are talking about a divide and conquer strategy, which inherently has two phases. There's the phase where you develop the components, in other words, the different damage repair approaches to repair this or that type of damage. And then there's the step where you put those things together in the same individual at the same time. Now, that second part, in the case of standard engineering, like when you're doing this for a car or an aeroplane or whatever, is usually pretty trivial. You can be pretty damn sure that when you put the components together, they're going to do the overall thing you were intending, just as long as the individual components work. But the thing about the human body is not only is it so much more complicated, it's also a machine that we didn't design. And, that has huge complexity that we don't know about yet, we don't understand yet. So that means that the putting the things together part is very likely to throw up a bunch of surprises. Some of those surprises may be pleasant ones, where things work more easily than we would have expected, but some of them may be unpleasant ones, where, for example, things that we thought were going to synergize actually cancel out. So, in my first two organizations, the LEV Foundation and Science Research Foundation, I was pretty much entirely focusing on step one, on developing these various interventions. And in particular, I was focusing on the most difficult ones. Of course, different types of damage are not necessarily equally easy to fix, and sure enough, there's some that are quite hard. And the hard ones are being neglected by other people because, other people are laboring under short-termism constraints. They've got to get a publication out in a top journal every 10 minutes, or they won't get their next grant application funded. Or in industry, they've got to satisfy their shareholders. Anyone who wants to make money wants to make it tomorrow. So I am pretty much the only expert in the field who is in the fortunate position of being funded entirely by philanthropy, and therefore without these short-termism constraints. And I very much leveraged that over many years to work on these more difficult types of problem. And that was successful. We were able to take various very challenging projects through to a point where they had sufficient proof of concept that we could spin them out as startup companies. Did that half a dozen times. And those companies are, mostly thriving and doing and pushing things forward. And that was a very deliberate strategy on our part because the fact is investors write bigger checks than donors do. And so progress was accelerated. But now we are in the position where the easier types of damage, the lower hanging fruit that I never worked on because other people were working on them, those things have, in some cases, over the past just few years, 3 or 4 years, have reached the point where they just about work in mice, right? So one can take middle-aged mice and do something to them, and they'll live a bit longer than they otherwise would. Now, this is extremely good news for a bunch of reasons. The first reason is it kind of, let's say, attenuates, reduces the strength of the argument I just made that this is a divide and conquer approach. In other words, what we're seeing is that an individual intervention that repairs one type of damage can have knock-on effects, indirect benefits that maybe just slow down the accumulation of other types of damage, or maybe even repair other types of damage vicariously by essentially strengthening the inbuilt automatic repair machinery that we have for some types of damage already. All right, so what this all means is that if we start trying to take these individual therapies that seem to have a modest effect already, individually, and we put them together in the same mice at the same time, then we may very well get a synergistic effect, an additive effect, where you get a substantial increase in lifespan. So that is the focus of LEV Foundation. It may not be the focus of LEV Foundation forever, but it is now. And so as soon as I was able to get the foundation going and pull together enough money, I started the first study, which was just on 2 years ago now, February of 2023. And that study is very nearly done at this point. It's a study that nobody else was in a position to do. First of all, it cost quite a lot of money, $3.5 million. Second of all, I needed all that money, almost all of it anyway, at the beginning, because the main costs are, first of all, you've got to buy middle-aged mice. They cost a few $100s each, and I need 1,000 of them. And secondly, you've got to do these interventions, and they're damage repair interventions. So by and large, we were doing them once at the beginning of the study. And they each, there are cell therapies and gene therapies and such like. So these are things that have very substantial costs in terms of not only the reagents, but also the manpower. And that's a part of the reason why nobody else is doing them, even though there is a great deal of expert consensus that the study I've been doing is extremely valuable. So that's what we do at LEV Foundation. We do these combination, late onset, middle age onset, rejuvenation, damage repair studies in mice. And we are seeking to extend mouse lifespan, of course, by extending healthy lifespan. We measure all manner of things that are determinants or measures of the health of these mice, not just how long they live. But at the end of the day, how long they live is the acid test, the readout that most people care about.
So these low-hanging fruits, and what are those that you're studying now, and how are they correlating to the types of damage that you outlined many years ago?
Right. So there are three in this study, and we combined those three with one intervention that is not damage repair, but which is so established that we wanted to see how it dovetailed with the damage repair ones. So the one that's not damage repair is rapamycin, which is a calorie restriction mimetic, among other things, and has in the hands of many research groups, it's been shown to extend life even if you start late in life giving the thing. That's the one exception to what I just said about doing everything at the beginning. We give the rapamycin to these mice throughout their lifespan until they die, starting in middle age, starting at 18 months of age. So the other three, what we did was, first of all, telomerase gene therapy, then a senolytic, and then young blood stem cells. So three very different things. A senolytic, well, I think most of the audience probably knows what that is. It's a drug that selectively kills cells that have got into this aberrant zombie state called senescence, and which accumulate in the bodies of humans and mice, essentially because the immune system is fairly good, but not perfect at getting rid of them when they arise. And they are not just zombies, they are actively bad for you. They secrete chemicals that are toxic to the rest of the body. So if we can get rid of them, that's good. People have shown that if you do that, then you get, extension of life in certain models anyway. Then telomerase gene therapy. Well, everyone, I think, probably knows what telomerase is. It's this enzyme that extends the telomeres to compensate for the shortening of telomeres that happens during cell division. It's actually a little bit paradoxical that mice benefit from telomerase overexpression because they make their own telomerase much more promiscuously than larger animals like humans. But they're so terribly bad at the maintenance of their DNA, especially at the telomere, that it turns out that having a bunch more telomerase is worthwhile anyway. And this was first shown about 10 years ago by Maria Blasco's group, and it was shown more recently by George Church and Liz Parrish. So there's good prior art showing that this actually is beneficial. And then with regard to young blood stem cells, so of course the concept of parabiosis has very much taken the world by storm gerontologically for the past 20 years, since the convoys in Tom Rando's lab and Irv Weissman's lab were able to show that it rejuvenates old mice, and that had moved on, partly as a result of work that we funded, actually, into the world of plasma exchange, where we, instead of connecting mice together surgically, we take plasma out of a young mouse or a lot of young mice and pump it into old mice. And that's all very well, but it's only the plasma, not the cells. And so other people have been thinking, well, maybe we shouldn't ignore the cells. The cells may matter as well. And so what they did was they did a bone marrow transplant. They basically, killed a lot of young mice, got a bunch of their bone marrow, purified the stem cells, and injected them into old mice in a manner that allowed the young stem cells to engraft and become permanently resident in the bone marrow of the old mice. And sure enough, that also worked. A couple of studies have been done over the past few years that have shown good results in terms of extending lifespan that way. So those are the three things that we combined this time, plus rapamycin.
And what has been the result so far?
So I'm pretty happy with the results. We haven't, completely knocked it out of the park, but we've definitely shown that these things do have additive effects. And the combined additive effect that we can get is about the same as what people have achieved in the past with calorie restriction starting at that same kind of age. So we're talking about roughly 4 months of postponement of health problems and postponement of death. The thing we would like to do, and which I feel very confident that we can do soon with a few more of these studies, is to break through that barrier. Calorie restriction, of course, has been a phenomenon that's been the extension of life through calorie restriction has been known for nearly a century at this point. And, people tried it in middle-aged mice 40, 50 years ago, and that's what they got, 4 months. We can get pretty much the same with rapamycin on its own, because that's a calorie restriction mimetic. It basically induces the same kind of gene expression changes, some kind of metabolic reprioritization, shall we say, that calorie restriction itself causes. And that's great, but nobody is ever going to get a calorie restriction mimetic to do substantially more than calorie restriction itself does, precisely because it is activating the same pathways. So, it can't do any more. Whereas damage repair, in principle, could. So, as I say, we haven't done it yet, but we are, pretty happy that with just 3 damage repair interventions, we got a very substantial signal. And so, the next study I want to do, and future studies, will involve at least twice as many, probably 7 or 8 damage repair interventions, plus also rapamycin. But we're just going to give rapamycin to absolutely every mouse rather than testing how it jives, because it's proven now. And we might do other things like that. So that's basically the plan.
But could you clarify? Have you seen this additive effect?
Yes.
Yeah.
Yeah. So it is complicated. I told you that we used 1,000 mice. That sounds like a big experiment, and you're damn right. But that's because that's what we're doing it in both sexes, so 500 males, 500 females. Second of all, we have 10 different treatment groups. We don't simply have one group that's getting all the interventions and another group that's getting none of them. We also have 4 groups, each of which is getting just one of the interventions, so as to somehow validate, make sure that we are indeed recapitulating what has been published by other groups in the past. And then, in order to get the information we need about interactions, and in particular the bad news that I was talking about earlier, the possibility of cancelling out between things, we have groups that are getting all but one of the interventions, 3 out of the 4. So that's another 4 groups. So each group per sex has 50 mice, and that's about as low as you can go and still have reasonable statistical significance given the kind of signal, the kind of effect size that we expect to get. So, if you look at our results, you'll find that you have to be fairly sophisticated about the details. The study's not over, so I haven't yet done the rigorous statistics. But what we can certainly say is that males and females behave very differently. Females are the ones that are easier to interpret, and you can see all this because I post, interim results, the survival curves as they currently are, to the web, to social media every month or 2. My last post was less than a month ago. So In females, it's pretty clear. The group that's getting all four of the interventions is living about 4 months longer than the group that's getting none of them. Sounds great. And the groups that are getting one or three are in the middle. Now, there is still plenty of scatter because, that's what you get with only 50 mice per treatment group. So the curves don't go in lockstep, staying all in the exact same order. But the broad story is, yes, we're seeing additivity. In Wales, it's a good deal messier. In particular, during the early parts of the study, basically through 2023, um, some of the treatment groups were doing considerably worse than the control group. The groups that were getting one or three were doing considerably worse than the group that was getting nothing. Um, it kind of all sorted itself out in the end. Certainly, the group that is getting everything is doing better than anyone, at least as well as anyone else. Um, but yeah, I memean, it's a more complicated story.
Do you have any idea why that is?
No, to be honest. This is what we're going to be doing. One big advantage that we have is we didn't have the in-house capacity to do this experiment, so we worked with a CRO. But we didn't work with any old CRO. We worked with a company named iCore Life Sciences, which does other things in addition to being a CRO, I should mention. But the key thing about iCore is that it's one of our spin-out companies. It's led by one of my early proteges, Kelsey Moody. The staff are fantastic. They've done a lot of lifespan experiments before in mice, though not ones on this scale. And they totally stepped up to the plate and were able to do everything we needed to do. And we had weekly calls with them until a few months ago, anyway, to discuss any anomalous things, any potential, changes we might want to make to how the study was being done, things like that. So we are, we're very happy with how the study went in that way. In other words, that we had full information about what was going on. If you work with a CRO, normally you just pay them a bunch of money and you hope the results are believable. We didn't have that. But what we will probably do over the next month or two is we'll go back and analyze the more anomalous results, especially in male mice, and try to come up with some hypotheses for why we saw what we saw. But that hasn't happened yet.
Aside from adding more interventions in the second round or the second study, would you also be interested in having even larger cohorts, like 100 mice in a group?
Well,
I mean, it's incredibly difficult. I understand that, but to get more statistical firepower, so to speak.
Yeah, I mean, of course, eventually you hit diminishing returns as you increase the sizes of the groups. I think honestly we've probably got it about right. The difference between if you've got twice as many mice doing essentially the same number of interventions with treatment groups that are twice the size versus doing twice as many interventions with treatment groups that are the same size, I would definitely go for the latter of those as the one that will give us more information.
We had Yuri Dagin. He's the CEO of Youth Bio. He commented on social media on your latest results. Monumental effort by Aubrey, but the results make me quite sad. All we could squeeze out of these interventions is just 10 to 15% lifespan increase. And even then, rapamycin alone can produce that much. And then, of course, he talks about partial reprogramming, which is his field. What's your comment to that?
Well, of course, whether one is pleased or disappointed is more subjective. The results are what they are. I'm personally pretty pleased because even though we have not knocked it out of the park and broken through the world record achieved by calorie restriction yet, I believe that the overall message from this study is that we have a very good chance of doing so in the future. We are seeing additivity and so on. As regards partial reprogramming, absolutely, it's a big deal. And we are now in a position which we were not in 2 years ago when we started the first study. Namely, people have reported genuine life extension using partial reprogramming on its own in mice. So our firm intention is to include partial reprogramming in our next study. Um, the Yeah, I mean, that's where things stand. We know that we're going to need more interventions. I mean, Yuri called it a monumental effort. It really wasn't as monumental as I'd have liked it to be.
Sure.
Of course, we were constrained by budget, as we always will be. The sooner somebody writes me a large check, the sooner I'll be able to do studies that are on the scale that I'd like to do. But yeah, I think what we want to do is simply show that these studies have enormous value. In fact, I would say that they have by far more value in terms of information acquired per dollar spent than any other studies that anyone's doing in the whole field right now.
And you're still maintaining that there's a 50-50 chance of reaching longevity escape velocity in 12 to 15 years. Is that correct?
That's correct, yes. Honestly, I'm very happy that time frame, getting there in the late 2030s, has not really slipped at all, my predictions, for the past 10 years. If you look at the previous 10 years, there was plenty of slippage. When I started giving time frame predictions, that was '04, and I was basically saying around 2030. So it's definitely slipped, by several years. But all of that slippage happened in the subsequent 10 years until up roughly the Hallmarks paper, because after that, suddenly I no longer have to justify the damage repair approach to other people. And, investors started coming in, lots more money came in. The money is still outrageously unevenly distributed. So there are definitely things that are lacking in terms of funding, but it's so much better than it was. And that is the number one reason why my timeframes have stopped slipping. Now, I would say, honestly, they are beginning to slip again because we haven't got the money to start the next study. I should have started the next study a year ago, but we haven't got the funds because, as you know, the funds that were donated to my research in 2021 are not available to me.
Yeah. But let's take this 12 to 15 years. What kind of milestones do you foresee on the way to longevity escape velocity? What do we have to reach incrementally on the path there?
Yeah, yeah. So the answer to that question, is very simple. We have to get to RMR. We have to get. So I've defined robust mouse rejuvenation as getting 12 months of delay in the health decline and the death of mice in an experiment of the sort that we're doing here. And as I mentioned earlier, the current record is 4 months. So what we'll be doing is trebling the current record. Now, that might not be so impressive if we had been making steady progress in the past. But as I mentioned, we haven't. We've made zero progress in 50 years. Yeah, I mean, it's like, you know, so that's very, very important in terms of what experts are willing to think and publicly say. I've been giving these time frame predictions for 20 years, as I mentioned. Basically, nobody else has. In fact, I've been berating my colleagues for not giving time frame predictions for literally 20 years. I wrote a paper in like 2004 on this. Um, uh, a couple of them, David Sinclair, George Church, have been kind of just about putting their toe in the water now. Talking about tentative time frame predictions. Of course, any prediction of this nature with any pioneering technology has to be probabilistic, and you've highlighted that already. But if you don't give anyone any time frame prediction, then people are just not going to believe you. They're going to believe that you don't believe yourself, right? And they're not going to give you any money. So it's a joke. So yeah, so RMR is what we need to get to. And the reason we need to get to it, I'll come to in a moment. But first of all, how soon do I think we're going to get there? I think we've got a 50-50 chance of getting there in about 3 years, just so long as I get that money in the door to do the experiments. I think we're talking about, maybe 3 more of these studies done bigger, probably done in parallel, so that we can get them all done in 3 years, right? Um, uh, all right. So then what? Well, this is the thing. I believe that things are going to move extremely fast from that point. first thing that's going to happen is, well, experts are going to come out and start saying, yeah, you know what, we're in a new world. We are within striking distance of bringing aging under genuinely comprehensive medical control. They probably won't exactly say, yes, Aubrey de Grey was right all along, but they will say something that equates to that. Um, and influencers are going to hear that. What makes an influencer an influencer? Or in particular, what makes an influencer remain an influencer for long? The answer is being right. Identifying when something that matters to people is changing, when the expert opinion on this thing is changing. And they get ahead of the conversation. And, that's what they do. So that's what's going to happen as soon as this change in the publicly stated opinion of experts happens. And I'm talking a very small number of experts. I'm not talking about the hangers-on. I'm not talking about the commentators like, Peter Fedichev, Bryan Johnson, whatever. I'm talking about the people who actually are overseeing this kind of work and who have been doing it all their lives. So, David Sinclair, Brian Kennedy, Matt Kaberlein, Eric Verdon, Nir Barzilai, George Church. That's about it. If we ask for people who, A, are recognized thought leaders in the field, and B, they are reasonably public figures. They go out and do a lot of, that's about the whole list. And of course, we know each other very, very well. So I am very sure of what it's going to take to get these people to feel that they've got, if you like, permission to go out and say much more gung-ho things than they're currently saying, without impairing their own funding from the government or whatever. All right. So what's going to happen after that? Influencers are going to say, you know what? Now's the time to actually advocate for a war on aging, a proper war on aging. I don't mean like a war on cancer, which was imperceptible drop in the ocean. I mean like the response to COVID, but on steroids. Something huge. People are going to say that. And the thing is, influencers are called influencers for a reason. They have influence. They change public opinion and public, choices. So, the following week, the public are going to be starting to escape from, wake up from what I've called the pro-aging trance, this, terror of getting their hopes up that translates into these ridiculous arguments that aging is some kind of blessing in disguise. They're going to start waking up and saying, let's do this. This is killing, 30 World Trade Centers every day. That sounds like a bad thing. Right. And of course, the minute the public start clamoring for this, governments will do what it takes. Because, there's only one priority that any elected person has, and that's to get re-elected. So, what will the governments do? Well, most people will look at my timeframes and they'll say, wait, you're saying that it's going to be like around 10 years from reaching RMR to reaching LEV. And they're going to say, you're absolutely off your rocker because, you know, look at how long it takes to get one drug through the regulatory process. But that is, of course, the point. That if we're talking about COVID scale or more, then we can use COVID as a precedent. We know all the numbers there. We know that there was a full order of magnitude reduction in the time it took from discovery to dissemination of a vaccine, relative to what had ever been done before. I think we'll probably see more than an order of magnitude in this case. So yeah, anything that you think you know about why things go slowly now, you can totally forget.
You mentioned a few names there: Eric Verdin, Matt Kaberlein, Nir Barzilai, Brian Kennedy. I think Brian Kennedy is pretty... I shouldn't put words in his mouth, but I feel like he's more optimistic than some of the other names you mentioned there. But are there a lot of people that are more health spanners, so to speak, in public that are saying different things in private?
You have to listen very carefully to what people like that say in public. In particular, what they're actually doing is not, in general, putting themselves on the line. As I say, David and George have gone as far as to make tentative timeframe predictions. The others haven't even done that. 18 months ago, Bryan and I worked on this thing called the Dublin Longevity Declaration. It had that name because we launched it at my conference in Dublin. And it's a considerably more aggressive statement than anything that had come out prior to that. But it doesn't really have timeframe predictions in it, not proper ones. And that's because that's as far as we could go at that time and still get people to sign. We got like a couple of hundred of the top luminaries in the field, including pretty much everybody I just listed. I think absolutely everybody I just listed. Um, um, so that was great, but we wouldn't have got them if we'd tried to go further. It needs more data. It needs achievement of RMR to get them to say more. Uh, so Eric Verdon is a bit of an outlier among the group that I mentioned. And he doesn't really have much of a choice because he doesn't just run a lab. He runs an entire institute, and that institute gets half its money from the government. In other words, through peer review, which means that Eric, I mean, in private, yes, he is somewhat more pessimistic about timeframes than I am, certainly, probably than most of the people I listed. But he's every bit as hopeful as the rest of us that he can be wrong, that we actually will make fast progress. And so he and I are completely aligned when it comes to, well, very closely aligned anyway, when it comes to what our research priorities are. He was almost in a position to do experiments very like the ones we're doing at LEV a couple of years ago, until the funding got yanked at the last minute. But yeah, I mean, so we're very much on the same page when it comes to what research needs to be done and what we hope the outcome's going to be. And divergence at the level of how soon we expect a certain amount of progress to be made really is irrelevant.
Mm. Yeah, this contrasts nicely with what I'm going to bring up now. So Patrick and I, we were at the Longevity Biotech Fellowship Retreat in Sweden just about a year ago now. And it was quite surprising to find that the organizers of that retreat, among those Nathan Cheng and Mark Hamalainen, they were not talking so much about any hallmarks of aging or the sense approach. They were more interested in what's called the replacement strategy, and also talking about advanced bioengineering on a scale that I hadn't seen at that point before. And we had Mark Hamalainen on the podcast recently, and he felt less optimistic now than he did 20 years ago, because he said that we have still zero aging interventions. And he's also not so sure that your approach is the right approach. I know that you are very much a fan of the Longevity Biotech Fellowship and have helped them in the past, I believe. So how do you reason about this?
Right, yeah. So, yeah, let's go through this in some detail because there's plenty to say. You're quite right. Mark and I are very close friends. He was one of my early proteges. I funded his PhD before he dropped out. We've been, and I, as you say, I seed funded the in real life part of the Longevity Biotech Fellowship when it was called Less Death a couple of years ago. And I have huge admiration for what Mark has done in that area and is continuing to do. I feel that it's a very, very important way to bring newcomers in and get them mobilized in an impactful manner. So you're right that Mark has got very enamored of the replacement approach. So let's go through and talk about what that is and what I think about it. First of all, let's talk about organ replacement. So I've always said that when we get to longevity escape velocity, it will be, very much version 1.0. We will only just be there, and there will be some bits of rejuvenation that don't work very well. And in particular, I've always said that we're probably initially going to need to do surgery for some of it. In particular, we're going to need to do organ replacement. We're going to need to, transplant artificial organs in order to, you know, achieve the effect that we can't yet achieve by doing more microscopic damage repair. But that since we don't really like surgery, and it's daunting and perhaps risky, that will be a short-lived period, and we will move rather rapidly to being able to fix everything at the level of cell therapy and so on. Um, uh, However, it will be an interim situation. So the thing that's relatively new in this area, in terms of actual nuts and bolts biology, people actually doing things in the lab, is the idea of going one step beyond organ replacement and replacing the whole body. How would you do that? Well, you've got to get one. Now, there are two ways to do that, just as there are for organs. One is you can get a whole body from somebody who's dead, and there has been plenty of talk about that for quite a few years, in particular led by a surgeon from Italy named Sergio Canavero. Um, or you can grow one in the lab. Now, that sounds crazy, but it turns out to be relatively straightforward in principle to grow a body that doesn't have a brain, which isn't really a body. And this happens naturally. People have genetic defects that cause them to develop in a manner that doesn't have a brain, and those people are legally not considered people. So, their life support is turned off and so on. So the idea is if one could just do this in a kind of routine basis, grow a lot of such bodies, one could potentially attach somebody's head or somebody's brain to this young body that was, biologically much younger than the person whose brain we were transplanting. So you could call it a whole body replacement, you could call it brain transplant, you could call it body transplant. People use different ways, but it all amounts to the same thing, really. Now, um, so what do I think about this? Well, let me first talk about the technical side and then the social side. On the technical side, it can probably be done, but it definitely can't be done anytime soon. Partly because there's a lot of technological things to get right. Growing a body outside a womb, in particular, keeping it alive for a long time. That's hugely expensive, very tricky, challenging technology. But also because you can't speed it up. Once you know, an anencephalic baby is born, even if they are taken to term, you know, through a surrogate mother without any kind of incubation, nevertheless, you can't attach an adult brain to that body until that body has grown to, adolescence kind of level, and you can't speed that up. So if one is thinking about one's own potential to benefit, and if one is Mark's age, then one might think, well, this is probably going to be possible in time for me. Um, and we can come back to the pros and cons of Mark's pessimism about the more divide and conquer approach in a moment. But the thing is, I've already highlighted one way in which Mark and I somewhat depart, and not just Mark and I think I am somewhat in the minority among the longevity community here. I really don't think very much about myself. I think mostly about humanity. And therefore, I want to save as many lives as possible, whichever lives it turns out that happens to be. I do not think in terms of, only prioritizing the things that have the greatest chance of benefiting me myself, or indeed my loved ones. I think in terms of humanity overall. So it seems to me that we have to take into account the timeframes if we want to save people who are, my age rather than Mark's age. On top of that, we have to make sure that we are able to achieve large-scale uptake of this, or else we won't be helping humanity. So first of all, we're talking about absolutely astronomical expenditure to grow all these bodies. And second of all, we have to worry about whether it's going to have too much of a yuck factor, whether it's just not going to happen for people to say, okay, yes, I'll take this body. Now, I'm not too worried about the yuck factor side of things because we will have time for humanity to kind of, get used to the idea, and to come to terms with the idea that there's really no ethical issue here. But still, it's damned hard. And I, so this is a large part of the reason why I don't really agree with Mark in terms of the of what could be done.
Can
But
I say something there,
well,
Aubrey? Just to interject there. I mean, you've read the Replacing Aging by Shauna Bear, of course, and you know what Mark says. I mean, their argument is that this is actually setting aside the social thing. Their argument is that this is actually the faster path than trying the divide and conquer approach. So
right. So that's
it
why,
would be. I think we're setting this up for a future debate because I think this is worthy of two experts talking about this. I'm just the novice here.
so that's where I was going next. Um, so first of all, we have to complete the part of the question that revolves around how hard replacement is. And the part that I haven't dealt with yet is the brain. Everything I've said so far revolves around the body. So we're thinking about putting an old brain into a young body. Now, we have no idea at this point the extent to which the young body will be able to rejuvenate the old brain. It could be that it doesn't rejuvenate very much at all, that most of the things that make the brain go downhill are autonomous, and simply cannot be or will not be significantly slowed down or let alone reversed by the attachment to a young body. Now, interestingly, at this point, Mark works for Jean Hébert at Upper
Yeah, that's right. At
Um,
ARPA age.
that's right. And Jean Hébert, who, of course, came up, I guess, in the conversation with Mark that you had,
Yeah.
um, is a neurologist. He focuses on the brain. So he's not been focused so much on the whole body replacement part. He's left that to other people. But he is himself rather pessimistic about the ability to rejuvenate the brain by molecular and cellular means. So he wants to use surgery for the brain as well. And that is a whole different kettle of fish because the brain is the location of our identity. And if you replace the whole brain in one go, so it's not like replacing the liver in one go, it rather defeats the object. So, of course, there are parts of the brain for which this doesn't apply because they do not contain long-term memory and personality and so on. The hippocampus or the hypothalamus or whatever. And people have been looking for quite a long time at ways to replace them with artificial or artificially grown replacements. But if we talk about the neocortex, where identity is, then you've got to do something better than that. And so Jean's idea is to exploit a phenomenon that has been well documented over many years, which is that the location of particular parts of identity, particular types of memory, for example, is fluid. That if that everything is stored in a kind of holographic way, a distributed way, different things are stored in small regions of the brain. Like there's this part of the neocortex called the visual cortex, and that's where certain things are stored. There's other place called the auditory cortex, and so on. But there's various good evidence that one can relocate types of information from one part of the brain to another, essentially by gently inactivating the part where the thing currently is. This has happened naturally in the case of benign tumors, which gradually eat away at parts of the brain. And for example, someone can lose their entire language center, and yet they can still speak because the information that enabled them to speak English or whatever um, just moved. However, Jean recognizes and freely acknowledges that there is another criterion that is required for this relocation. It's not just that the place where the stuff currently has to be gently inactivated to give, if you like, time for this to happen. But it's also that the information has to be used. Only information that's actually retrieved into consciousness is actually relocated by effectively being rewritten in the new place. So, for example, if I'm subjecting myself to this inactivation of, let's say, the place in the brain that stores my knowledge of the capital cities of countries, right? And supposing that process takes a month, right, of inactivation. And during that month, somebody asks me what the capital of Venezuela is, and I remember that it's Caracas, and I say that that gets rewritten in the new place that's not being inactivated. Bang. But if I am not asked during that month what the capital of Colombia is, then I will come away from this month not knowing what the capital of Colombia is. And of course, I'm giving a rather, frivolous example, but you can very well see that, there's a lot of information that one considers part of oneself, like, names of one's old friends, things like that, that one's going to lose because one doesn't actually think about it more than once a month. And Jean says, well, yeah, I'm afraid that's true, but it's the best we've got. It's the best we're going to have. So we have to come back to the question of, is it the best we're going to have? Now, if you go through Replacing Aging, Jean's book, or indeed other things that he's said and written, you will find that he has thought about this. He has specific examples of the kind of damage, the molecular and cellular damage that accumulates in the brain, that he believes is, really, so difficult to repair at the molecular and cellular level that we might as well regard it as impossible to repair, and therefore we've got no choice. And that's where Jean and I differ. I believe that everything we're doing to develop molecular and cellular repair in the rest of the body is applicable to the brain, and without all that much additional sophistication or modification. And therefore, yes, we should absolutely still be going hell for leather trying to achieve that so that we don't have to make this compromise. And that brings me back to Mark, because Mark, as you've mentioned, is focused on the rest of the body, and the same applies. So honestly, I'm a bit surprised that Mark is coming out and saying, well, his pessimism arises from the fact that we still have no anti-aging drugs. I think that's a crazy thing to say, because we know that it's a divide and conquer strategy. Of course, we don't have them yet because there are some bits that we don't yet, and we haven't yet developed. But there are some bits that we have, and we're getting to the point where enough of the bits that we have developed, can be put together to actually achieve significant life extension in mice. Which is, still means we've got another ways to go before we can do the same thing in humans. Don't get me wrong. But that's what leads me to be continuing with my own timeframe estimates. And I think that Mark and Jean would definitely agree that there's less than a 50-50 chance of achieving whole body replacement that's actually available to people by the late 2030s. So, in other words, their view of what we should prioritize is based not only on being really rather optimistic, I think too optimistic about how you do replacement, especially of the brain, and also on being what I view as unreasonably pessimistic about the molecular and cellular approach.
They have this technical plan to solve aging, and cryonics is a part of that, and that's not really a solution. That's just hitting the pause button and hoping that we will find a way in the future. And then replacement, as you've explained now at length. And then they also have this advanced bioengineering side, which sounds to me that is the closest thing to what you're doing, but it seems that they want a more granular understanding of aging and much better tools than we can foresee now to actually solve this problem. But maybe you can explain that as well? What they mean by advanced bioengineering and why your approach wouldn't be enough
Well, so
in their view?
it's not really a difference of approaches. What they're really saying is, well, okay, look, we haven't got anything that really works yet. Therefore, there must be a reason why we haven't. Maybe we're just not being sophisticated enough. Maybe we need to know a lot more, understand a lot more about how the system works um, in order to be able to repair it in this way. And of course, this is fine. It's a difference of degree in terms of what we think. They're certainly not saying that it's impossible because you would have to understand the system completely. They agree with me that there's a certain amount of understanding that would be enough. It's just that they currently feel that that amount is greater than I think it is. But at the end of the day, as with any system like this, you don't know that you know enough until the things that you try to do with what you know are, tested. And either it works or it doesn't work. If it doesn't work, then that basically says you didn't know enough. Uh, so you just have to try. And at the moment, I think we're definitely in that position. Of course, to some extent, we are already developing those much more sophisticated tools, especially at the in silico level, at the AI level. And my main problem at the moment with that aspect of the field is that too many people are getting too optimistic. They are saying, okay, AI is moving so fast that it's just going to solve this for us. And Mark has exactly the same view as me on that. He thinks that it's ridiculous to place our faith in that. My view is that, yes, AI will increasingly accelerate what we can do relative to what we would be able to do without AI. But in order to get the maximum out of this, we have to give AI the right data. And at the moment, we've got certain types of data that we can give it in large abundance, omics data from people of different ages and things like that. But we've got other types of data that we can't give it at all. In particular, we can't give it data on how long mice live when you give them a bunch of rejuvenation, right? So we have to do the experiments of the sort that LEV Foundation is doing in order to give AI a starting point.
I think we'll get back to artificial intelligence. Before we do that, I'm interested in the debate you had with Peter Fedichev. He has this other theory of aging, which is not too easy to understand, at least not for me.
So it's not really a theory of aging. It's not even really a difference between myself and Peter with regard to what we think happens in aging. Now, saying that, it is more or less the same thing that David Sinclair has called a theory of aging. He calls it the information theory. But let me just, take the word theory out of this because I honestly believe that it's a counterproductive word to use. Uh, what Peter is saying, and indeed what David is saying, is that one of the important types of damage that accumulates during life is epigenetic noise, essentially randomization of the decorations to our DNA that determine which genes are turned on and which genes are turned off and when and under what stimulus and so on. Of course, all of our cells, to a first approximation, have the same DNA. And therefore, the reason why some cells are brain cells and some cells are liver cells and so on is because of that epigenetic information. The epigenetic information that has been most thoroughly studied thus far is something called methylation of cytosines in the genome. This is certainly a very big part of it, but it's only one part. There's also modifications of proteins called histones. There's higher order chromatin packing, as it's often called. There's lots to go on, but we can stick to methylation for the moment for this purpose. All right, so methylation is laid down, and that tells a cell what kind of cell to be. Now, if there is noise in that, if some of that gets randomized, then the cell becomes less sure what kind of cell it's supposed to be. And it starts, making proteins it's not supposed to make and failing to make ones that it should make and so on. This is actually not a new idea. It was first put forward more than 40 years ago by a really venerable and wonderful gerontologist who doesn't get nearly as much credit as he should, a guy named Richard Cutler. And he called it the disdifferentiation theory of aging. Um, he was able to show that old brain cells make hemoglobin. That's not the kind of thing that brain cells are supposed to be making. But they start making it in low quantities late in life because the gene that encodes for hemoglobin gets reactivated to a smaller amount. This is the exact same thing. David has a particular mechanism for why this happens, or why a large part of it happens. But that again is not really the issue from that you're asking about, because you want to know what Peter said. Peter has come along and said, well, this epigenetic noise plays a much bigger role in the aging of humans, and indeed most species, than what it does in the aging of laboratory mice. The laboratory mice, basically get killed by other things before their epigenetic noise starts to matter all that much. And he's shown this in various ways. His papers on it are, they betray his past as a physicist. They have rather too many equations for your average biologist. But the fact is, that's the essence of what he's saying. Um, However, he's saying an additional thing, which is very much more controversial. What he's saying is that we can't fix this. That we might be able to stop aging by stopping this noise from accumulating anymore, but we can't fix it. Because in order to fix it, you would have to be able to look at the DNA and say, well, this methylation state of this particular cytosine is wrong. Let me fix it, either by methylating it or demethylating it. Whereas this one is right, we'll leave it the way it is. You'd have to have an oracle, if you like. Um, Whereas for the other kinds of damage that we're interested in aging, things like waste products, you don't need an oracle. It's a foreign thing that shouldn't be there. You just crunch it up or you excrete it or whatever. Um, and this is a very definite difference. Something that's enzymatically detectable versus something that's not. I mean, it's chemically detectable versus not. But the question we have to ask ourselves is, what harm does this epigenetic noise actually do? Another famous gerontologist from yesteryear named Robin Holliday gave this a name, actually. He called these things epimutations. And that word, largely thanks to me, actually has become kind of resurrected and people often use it now. So that's what it means. Now, my personal view is that epimutations do matter for cancer, same as actual mutations matter for cancer. And therefore, it's good if you don't have them accumulating. But if you do, then if you have really good ways of getting rid of cancer, then you don't have to worry about that aspect. And of course, I have various ideas for how to do that. So the question is, what about the mutations and epimutations that don't have to do with the cell cycle? That make cells divide when they shouldn't? And the short answer is, I believe they don't matter in anywhere near a currently normal human lifespan, simply because they are kept in check by the same machinery that keeps our cancer genes in check, that makes sure that we don't get cancer before we've reproduced. So this is a concept that I have called protagonistic pleiotropy. Essentially, everything that doesn't have to do with the cell cycle is protected unnecessarily well. All right. But still, damage accumulates. So we have to ask ourselves, does it matter? And Peter has done work showing pretty convincingly that it does contribute to decline in function. So we have to ask, what can we do about this? And the thing is, there is something that we already know we can do about it. We already have data, namely partial reprogramming. This is what partial reprogramming is. If we overexpress these things called the Yamanaka factors, but not too much, then we can reverse the developmental clock of cells just a little bit, make them more regenerative, and it seems to rejuvenate. It seems to actually make ours live longer and so on. So we have to ask why. Now, I believe that the answer is very straightforward. It is unaccessed informatic redundancy. That's the term that I've been using for this. Well, if you look at the kind of talks that David gives when he describes the information theory of aging, he talks about cells having a backup copy of their epigenetic state. Now, I think that's a very poor use of language because it makes it sound as though the backup copy is in some physically remote location. In fact, in his slides, I've told him this, in his slides he has, you know, he kind of implies that by the way he draws the diagrams that communicate this. But what it actually is, it's in the same location. It's just redundant. So if you think about a digital image, a digital photograph, it's made up of 1 million pixels, right? Now, if you randomize half of those pixels, then you're going to still be able to tell what the photograph is of, but it's definitely the quality is going to be degraded, right? So this is analogous to what actually happens with the epigenetic state of a cell. So now we ask, okay, how is partial reprogramming addressing that? And the answer is, we know what partial reprogramming does at the epigenetic level. It makes cells more stem-like, right? Um, so just like to put numbers on this, supposing you've got your cell that starts out in a youthful state being 100% a liver cell, okay? And then it accumulates noise. Let's say that it does what I just said. You've got half the pixels, half of the epigenetic state has been randomized. So this is now 50% liver and 50% random. Now, you bring in your Yamanaka factors. Now, the Yamanaka factors don't have an oracle. They don't know which CPG sites are random and which sites are liver. So they'll just stemify everything. But you don't push it too long. So let's say you stemify half the sites. So what have you got now? You've got a cell that's 50% stem and 25% liver and 25% random, right? And then you switch off the Yamanaka factors, and the cell looks at itself and says, what the fuck? Right. It realizes that its epigenetic state is damaged. But now, what is it in? It's largely a stem cell, so it knows it's got to differentiate to become some type of other cell. However, it's also 25% liver, so it knows what kind of cell it's supposed to be. This is the problem if you take reprogramming too far in vivo. The cells don't know what they should be, and so they become everything, and you get these strange cancers called teratomas with, teeth growing in the heart, things like that. But this cell does know what it's supposed to be because it's got 25% liverness. So it goes away and fixes everything that is stem-like to become liver again, because that's what differentiation is. It's already programmed into the genome to know how to become a liver cell. So what have you got at the end of that? What you've got is a cell that is 75% liver, because all the stem stuff has become liver, and you've still got the 25% noise. But remember what you started with. You started with a cell that was only 50% liver and 50% noise. So this is bang up rejuvenation. This is what I believe is happening with partial reprogramming, and it totally nullifies Peter's pessimism. It says we don't need to worry because yes, we've still got some problem, but not enough of a problem to make us sick.
Well, but Peter is certainly aware of what's happening with the partial reprogramming field now, but he still maintains his theory here.
Right. So when we talked about this, the debate that has been videoed and put on YouTube is a debate that we did in front of a relatively general audience at the Foresight Institute, and so we didn't get any further than what I've just said, essentially. But face to face, we have got a little further, and essentially we have not exactly agreed to disagree. We've agreed to disagree about about what's the truth. And the reason we have is because we have agreed that more experiments are required in order to definitively answer this question. It could be that there's some other explanation for why partial reprogramming works. And so it does remain to be seen. I'm not saying that this question is completely open and shut, closed, but I feel the evidence is very much, in my favor at the moment.
You explained this very nicely with pixels. How much do you use in your thinking about biological matters? Do you think in terms of pixels and computer language and the digital world? I mean, you come a little bit from that world.
Yeah. So early on, in my first few years, when I was learning biology and trying to understand what the real questions were, what the ones that mattered, and so on, it helped enormously that I came from a computer science background. I was kind of coming at the whole topic, the whole question, without being encumbered by the conventional wisdom of those who had spent their whole lives as biologists. And certainly, without that, it would have been much more unlikely that I would have come up with the realization that damage repair was much easier than slowing aging down. Uh, However, I think in more recent years, it hasn't really made much of a difference. First of all, that paradigm has caught on. Um, I mean, to some extent it does. Certainly, I feel that it comes very naturally to me to think in evolutionary terms, to understand the evolutionary basis for this or that phenomenon that we see in nature, or for that matter, to give evolutionary arguments that such and such a thing is not true. The most efficient way to test a hypothesis is to elaborate the hypothesis and say, well, okay, what would this actually require? And you find out that you already knew the hypothesis was false. Um, um, that kind of thing.
I'm sorry, Peter, if I'm jumping around a little bit there, but I'd like to pick up on what you said there about
Patrick,
thinking in terms of, yes?
Yeah, I mean, you haven't been able to say anything for 1 hour and 15 minutes now, so I think you're entitled to ask some questions here.
Yes. Well, no, yeah. So I was thinking. You mentioned thinking in terms of evolution. That some people would say, well, look, don't touch aging. It's a kind of an evolved trait of humanity. But of course, you could also think that it's something that evolution missed. What's your view on that?
So first of all, I think it's very important to understand that even if aging exists because evolution wanted it to, because it was good for us in the wild for evolutionary fitness, so the hell what? The fact is we don't like it. Um, we have other ways to enhance our evolutionary fitness, with technology. And so it doesn't matter. Now, one thing that makes the question important, however, is that if aging existed as a consequence of evolutionary intent, then we ought to be able to find genes that we could inactivate that would allow us to live healthier for longer, because they wouldn't be killing us anymore. And that sounds like it would be a lot easier than doing the kind of thing that I'm talking about, enhancing our damage repair mechanisms with medicine. It might not be so easy, though. One of the major proponents of the idea that aging is a consequence of evolutionary intent, Josh Mitteldorf, has addressed this question head on. And he said, well, actually, chances are there's a lot of genes that one would have to inactivate because aging is so important for evolution to have that it has made it difficult for mutations to allow cheaters to emerge that don't age. The reason it's important not to have that happening is because someone like Josh accepts completely that in the near term, aging is bad for you at the level of, so an organism that suddenly didn't age would outcompete organisms of the same species that do age. It's just that in the longer term, he contends that this would be bad for the species. However, honestly, this is an area where I agree with the mainstream that aging is definitely not a product of evolutionary intent. It's a product of evolutionary neglect. That's the form of words that Len Hayflick first used to describe it. That simply, it's hard not to age. You need a lot of machinery. Everything that we do to keep us alive from one day to the next requires us to be repairing most types of damage as soon as they are created. And the only reason we age at all is because there are some types of damage that are created so slowly that they're not bad for us until after we have reproduced. But if we wanted to repair them as well, we'd need additional machinery, additional genes. And since those genes are not selected for, because reproduction does the job, those genes have not evolved, and or if they existed already, they have mutated into oblivion. So this is essentially why extrinsic mortality determines intrinsic mortality, as evolutionary biologists like to say.
There's also the pleiotropic effects. I mean, we could have genes that are beneficial for us at an earlier age, and therefore evolution has selected for them.
Right. So it's important to understand that this is not an alternative to what I just said. It's not. It's a special case of what I just said. A lot of people get this wrong. So let me go into it briefly. So here what we're talking about is some gene or some pathway that is beneficial in early life, and it's actively detrimental in late life. The question is, why is it still on? And the answer is because evolution couldn't be bothered to turn it off. So this is kind of the mirror image of what I just said. Instead of a gene not evolving or not being maintained through evolutionary time, what's not evolving is the gene to turn it off. We definitely have examples in biology where there's a gene that's useful in adulthood and useful in early life and detrimental late in life. And it's sufficiently detrimental that evolution did take the trouble to figure out how to turn it off. Probably a particularly conspicuous example that's known about right now in this field is FSHD. This is a type of muscular dystrophy that is caused by a mutation in the gene that's supposed to turn another gene off. And it's been known about for quite a long time. It's high profile now because someone who suffers from FSHD is a guy named Chip Wilson, who founded Lululemon, the fashion chain, and who is one of the key funders of the Healthspan XPRIZE that was launched not long ago. So actually the Healthspan XPRIZE has a component that's specifically targeting FSHD. But yeah, so this is an example of how this does happen when the detriment late in life is sufficiently big. If it's not sufficiently big, then such a gene doesn't evolve.
I thought we'd take some time to discuss artificial intelligence. I mean, everyone hears about new developments every day or every hour, it seems now. We heard the Nobel Prize winner Demis Hassabis say in an interview not that long ago, it was right around the time he accepted the prize, I think, that he believes that there's a good chance that we're going to solve all diseases in 10 or 20 years. I mean, in some way that prediction is maybe not too far off what you're predicting, because if we can reach longevity escape velocity, we would probably be pretty good at solving most diseases as well. But he's coming from it from the AI side, and of course they made AlphaFold. So and you said earlier in this conversation that one of the things that we might lack is data. I know that I spoke to John Jumper, who was the other guy who won the Nobel Prize. He actually said that with AlphaFold 2, they could manage to reduce the amount of data they needed, but still make a better model. Anyway, Aubrey, what is your take on this development?
Yeah, right. So, as you said, I started out in artificial intelligence research myself before I was a biologist. That was back in the day when it was all symbolic, when people had completely given up on neural nets of any kind, doing anything of any significance. And that only changed maybe 10 years later when Geoffrey Hinton had the brainwave of hiring a postdoc who knew how to program GPUs, and so he was able to do experiments with very large amounts of data, and it all behaved rather surprisingly well. Demis and I have known each other for a very long time. He went to Cambridge, same as me, and actually I met him when he first came up as an undergrad. He was maybe 10 years younger than me, but we got to know each other very well because we were both interested in board games at that point. And So we've kept in touch to the best of our ability, though it's been a few years now. We've both just been too busy. I've spoken to him about this, and 5 or so years ago, he said to me that he thought that aging was a sufficiently easy problem that it wouldn't need AI. And I'm not sure whether he'll think that anymore. In fact, I'm fairly sure he wouldn't. But I mean, I've had the privilege to meet a lot of very smart people over my career. And so it's a pretty strong statement when I tell you that I think Demis is the single smartest person I've ever met. And we are extraordinarily lucky to have someone like that in such a high-powered and influential position in this field. But what I think about what you just said is very important. So if we go back to AlphaGo, um, that went through some phases. Um, the first phase, which was called AlphaGo, and which was the thing that first beat the world champions, was trained on a large number of expert games in the public databases. And it was able to find improvements on what people were doing, and it was able to play better. But eventually they did this thing called AlphaGo Zero, which said, okay, we're going to do the same thing, but we're going to not start with the experts. We're going to start with only the rules of the game. And so, of course, the program took quite a while to become better at Go than a 3-year-old would be. It was completely random for quite a while. But once it got its foot on the bottom of the ladder, it was able to keep going. And eventually, in fact, quite quickly, it was able to do better than the version that had started out being trained on actual games. So this basically said that the humans were in some sense a distraction. That kind of contaminated what the algorithm could come up with. But here's the really important thing. When Demis was speaking about this, he was very clear that it was not a mistake to start with the trained version, the version trained on expert games. That they could not have got the program to the point where it worked so well without the expert games, unless they had started with the expert games. They found out a lot of things about how to write the program.
Right.
And so what you're saying that John said about AlphaFold is the exact same story. Not surprising whatsoever. There's another aspect to this, though, that's perhaps even more profound, which is what types of data we're talking about. In the case of AlphaGo, expert game, bang. In the case of AlphaFold, PDB, the database of experimentally determined protein structures using crystallography. Bang, no problem. In the case of aging, you've got lots of different types of data you might lean on. And some of it's available in abundance. Genomes, epigenomes, transcriptomes, all manner of omic data, longitudinal data. And we can get much more of it pretty quickly, pretty easily, if we just throw money at the problem anyway. But that's only one type of data. And so we come back to something I mentioned half an hour ago or more, which is how poorly we understand the way that the body works. We can look at the genome until our eyes glaze over. We have no idea what it means at all, right? I mean, virtually none. We know how we can tell what protein is going to be translated from a particular DNA sequence, but we can't tell anything about the epigenome to speak of. About what you can tell a little bit about. How powerfully it's going to be expressed depending on methylation, as I said. Huge number of things we can't check. We can't understand. So we have to rely on the ultimate readout that we care about, which is, in this case, longevity, right? And we just don't have a fraction of the data we need on that. And especially, we don't have a fraction of the data that we need relating to interventions that are within our reach. In particular, combination interventions, the kind of experiments that we're doing. So Sam Altman, who is one of the AI believers and who also is one of the longevity believers, put $180 million into a company named Retro Biosciences. He's now moved on. My understanding, through the grapevine, is that Sam now thinks that AI is just going to do it all for us. And he's been asked about this kind of question, about, how it's going to get the right data. And Sam says, yeah, what's going to happen is the AI is going to tell us what experiments to do, and we'll do them, and we'll feed the data back, and so on. And he's right. That is what's going to happen. But the AI has to start somewhere. The more experiments that we do before the AI is clever enough to be able to tell us what experiments to do, the faster it's going to be able to tell us well what experiments to do. So this in no way diminishes the imperative to do those experiments right now.
Demis Hassabis also talks about creating this virtual cell to be able to simulate all the intricate dynamics of a cell, and that's quite the endeavor. But does that, if we were to create a virtual cell and to actually use it in a realistic way in silico, would that change this in any way?
It would change it a bit, but only a little bit. First of all, how close are we to that? I think there we also have to take into account how little we know about how a cell works. I'm very sure that AI can bridge our gap there, of ignorance to a large extent. But I think at this point, it's too early to be all that optimistic that we can just throw CPU at the problem and take the kind of thing we know already about how a cell works and extrapolate to everything that we don't know. I think that's still a little way away. However, even supposing I'm wrong, supposing it's imminent, then we've got to worry about how cells talk to each other, and we've got a lot of cells. So no, I don't think that the argument I gave a moment ago is all that much affected by that consideration.
I mean, some people in the longevity community calls this hopium, that we can just rest on our laurels and do nothing. But I can't really see it that way. I don't think, maybe there are some persons that think that they can just sit back and wait, but I think it's a great tool, right, to accelerate all kinds of science.
Right, exactly. I mean, Mark Hamalainen is one of the people who use this word hopium. So yeah, I think regardless of which biotech approach one feels is most promising, one can still agree that yeah, we mustn't rest on our laurels. The question is anyone resting on their laurels, and does it matter? And unfortunately, if the wealthiest longevists in the world rest on their laurels, then that slows things down quite a lot. So as I just told you, Sam appears to be one of those people right now. He's not, as I understand it, giving any more money to retro. He's not the only one. I mentioned, I think, about an hour ago that Eric Verdin thinks very like me in many ways, even though you might not think that by listening to what he says publicly, and that he was on the point of starting a series of experiments very similar to the ones that I'm doing at LEV Foundation until his funding was yanked. And the reason it was yanked was because the guy who was providing the money decided that AI would do it all for us and that we should just rest on our laurels. And so, he's putting his money into AI safety, making sure that AI doesn't kill us all before it saves us all, things like that.
I stand corrected. Yeah. Okay. We've mentioned XPRIZE Healthspan. I saw another interview with you. Maybe it was the Peter Fedichev debate. You made a presentation there. Well, you said that you have your fingerprints all over the XPRIZE Healthspan. Can you explain how your fingerprints got there?
Yeah, whenever you see the word Healthspan used by an organization whose reputation revolves around being radical, you know perfectly well that they're just thinking about marketing, right?
Yeah.
So, of course, they were never going to call it that, really, and privately they recognize completely that it's actually a rejuvenation prize, not a Healthspan prize at all, right? So that's why they're calling it a Healthspan prize. But you can look at the rules. You can see what they're trying to do. They're saying you win the prize if you achieve a 10-year or ideally 20-year reduction in biological age of a reasonably sized cohort of people with interventions that are administered for a maximum period of 1 year. So that is rejuvenation through and through. and that is indeed no accident. Peter Diamandis and I have been discussing how to do a longevity XPRIZE of some kind for at least 15 years. And for the longest time, we couldn't figure out a way to do it that, according at least to Peter's intuition, which has been very good on these things, would actually catch the right imagination, would leverage the XPRIZE philosophy, if you like, of, audacity and achievability. But around, I'm going to say 5 or 6 years ago, that changed. First of all, a guy named Sergey Young came along. He's an investor in the longevity space, and he was willing to write a check to the XPRIZE Foundation for $500,000. What is that for? For the longest time, the XPRIZE has had this policy that they don't even start thinking about a prize properly until they've got enough money to do it, to think properly. Essentially to do a design phase for the prize, which involves not only deciding what the rules are going to be, but also scoping out how they're going to market it, how they're going to look for the main prize pot, things like that. So Sergey wrote that check. And of course, because of my history with Peter, I was brought in very rapidly to be part of the early stages of decision making. A lot of other people were brought in at the beginning. There was a 2-day meeting at the XPRIZE headquarters in which a dozen different possibilities for what kind of prize to do were discussed. And essentially, that was when I started taking charge and, essentially rubbishing most of it and getting buy-in from the XPRIZE, staff that I was right. So I essentially oversaw the scientific side of the prize design for at least 18 months from then on. So we're talking about basically 2018, 2019, maybe 2020, I forget. So that's why it's a rejuvenation prize. Since that time, as they've moved more into the process of trying to get, the funding in, which of course they eventually did, and of course, since they also want to market it and get lots of people to compete and so on, I have deliberately taken much more of a back seat. But I am very much still on their scientific advisory board. I take part I critique things same as everybody else does. I'm absolutely overjoyed that they've been so successful in bringing in not only 500 or so competitors, but also other advisors who are very much more mainstream and, non-heretic than me, because that's what is necessary to make the whole thing a success, to have people who are well respected by everybody, as well as being very knowledgeable.
Do you like their criteria? They measure they aim to measure the functional outcomes with muscle degradation and cognitive function. And I don't remember the third one now, but do you like where they were going with this prize?
Very much, yeah. Cognitive, muscle, and immune function.
Right. Immune function.
Absolutely. Again, that has its origins in the time when I was overseeing or heading up the design. It's been refined somewhat, and I very much like it. The immune side of things still has some work to be done. It's actually quite tricky to assess immune function in humans in an ethical manner, but there are some ideas there. So you may see some slight tweaks to what they're saying in regard to that over the next few months.
What do you mean by ethical manner?
Well, I mean, you can't give people infections that are bad for them and might kill them, for example.
Yeah, right.
But yes, I mean, it's very important, and this is very much, a unanimous view of the scientific advisors and of the staff, including Jamie Justice, who runs the whole thing. We should be focusing entirely on function. It should not be biomarkers. I mean, biomarkers are very useful, but if they're biomarkers at the level of structure in some way, like epigenetic clocks and so on, they can be secondary measures. But ultimately, the acid test has to be on people who are already going downhill. They've got to be already in middle age or older, and who therefore can be measurably rejuvenated at the level of what they can do.
Yeah, I also like that. I mean, anyone can understand that what it means to have a reduced immune function and the risk of getting dementia and not being able to just do ordinary stuff because you don't have the muscle for it. I mean, it's we don't do enough of that in the longevity community. I feel. I think it's an ingenious way to put it.
That's not really true. There are very large, long-standing studies that do more or less that. The most important ones are the longitudinal ones. There's something called the Baltimore Longitudinal Study of Aging. There's another one called the Framingham Study. These studies have been going for decades, and they've followed the same people for a long time. So they have huge amounts of information of all of these types and others.
Yeah, I meant more on the communication side. How we you mentioned we shouldn't talk about biomarkers. We should talk about things that people actually understand, right?
Well, I didn't quite say that. But we can certainly,
okay.
Talk about biomarkers. Biomarkers are very important, and the better we get at developing biomarkers that actually do tell us, quickly whether a treatment and intervention is going to work in the longer term, as surrogates of a surrogate endpoint, the better, the happier I will be. So it's definitely an extraordinarily important area of research. But the question is, what are the wider world going to believe? If you go out and say, oh, yes, we have rejuvenated people, we've got these wonderful biomarker results, they're going to say, yeah, what the fuck? Yeah, who cares a damn about that? I want to know whether I'm going to get sick. Whereas if you say, we have got these people to be stronger, or to have better memory, or to have better defense against infections, then people will say, yeah, okay, I believe you.
Yeah, I agree. So let's revisit ARPA-H then. What do you think of that agency? How they're going about things?
Well, I mean, obviously, I'm extremely happy that ARPA-H exists. The time is now for that kind of money, if not more, to be spent on stuff that would simply, not be given the time of day at the more traditional government agencies. And of course, it's not just focused on aging, but the good news is that it is substantially focused on aging. So they've got this rather small number of people who have the title of program manager or program director, I can't remember which. And one of those people is Jean Hébert, whom we've spoken about already, and who is very much leveraging that position to make a difference. He's not the only one. There's another guy, originally from Britain, actually, named Andrew Brack, who is also very much focused on doing something about aging. And so one way or another, these people are going to make a huge difference to what gets done. Of course, there is an enormous trepidation right now with the unpredictability of the incoming administration. We honestly don't know whether ARPA-H is going to be, in danger of being just shut down. But we certainly hope not, because it's doing fantastic stuff.
Speaking about Andrew Brack, he's overseeing the Prosper program. They have this idea for a tame-like design where they're going to talk about intrinsic capacity. What was your reaction to that?
Yeah, I mean, it's definitely not the only thing that needs to happen, but it's got a lot of value.
Patrick, do you have anything that you've been wondering about?
Well, I think it's going very well.
You have Aubrey on. You have no questions for him. That's fine.
No.
Okay, I can keep going.
You're asking the right questions, and you're getting great answers. I mean, I guess we could talk a little bit more about what you think about the political state. You're coming to Germany to our Eureka conference this fall.
Yeah.
Do you follow German politics? Do you know anything about the state there?
So I know very little about German politics, but I know a little bit because Germany is one country that now has a single issue political party focused on longevity. And of course, they don't expect to get elected, but because of the way that politics is governed in Germany, if you just get a very small number of signatures sufficient to get on the ballot, even in one part of Germany, then you get nationwide advertising that happens. So they've done that. So yeah, there will, you will see my face on German television. And so I think that's great. Of course, it doesn't change legislation on its own, but it gives exposure, it educates the wider world, so that's all fantastic. In terms of politics more generally, and the generation of more political will, shall we say, to get shit done in this area, well, I've talked about how I want to do that in a really big way. We talked about that an hour ago. The idea of getting to robust mouse rejuvenation and thereby getting experts to induce influencers, to induce the public, to induce governments to have a proper war on aging. I still think that that's what we're going to need to do. But in the meantime, of course, there are other things that can be done that may, at least tinker around the edges of all of this. And there are two things that I think need particular attention. One is pop-up cities, or more precisely, special economic zones. So many people will know that Honduras has a law that says that there are certain places that have very substantial legal autonomy. These are called the ZEDEs, the special economic zones in Honduras. There are three of them. One of them is on an island called Roatan off the coast of Honduras, and it's called Prospera. And it is very much focused on biomedical side of things. They have a clinic that actually was already there and well established before Prospera existed. And they're doing more of that. They're getting companies to incorporate there and to relocate there. And essentially, the goal is to become a global hub of medical tourism. So this would be nice. Couple of issues. First issue is medical tourism is by definition only for people who have the money to be medical tourists. And so it's not for everybody. So really the way in which this could affect the world in general is through FOMO. It's through getting established jurisdictions to see what's happening and see people going to these places and declaring publicly that this was what they needed and they couldn't get anywhere else, and doing something with their own legislation and their own regulatory structures to fix that problem. But that's slow. And it's even slower when we recognize that these special economic zones tend to only be put in place in unstable places, unstable jurisdictions. So in particular, Prospera is under threat right now because the government that created it and created the legislation to enable it to come into existence was voted out a couple of years ago, and the current government is opposed to these things and has been able to get the Supreme Court of Honduras to say that they're unconstitutional. So basically, Prospera is under extreme threat at this point of being just closed down completely. And the basic strategy, as I understand it, is to struggle on until basically November, which is when the next general election is, and when they hope that the original party will be re-elected, will be returned to power, and everything will be fine. But they recognize that if that doesn't happen, then they're done. So people are looking around for other special economic zones to do this kind of thing in, and nothing has really, blown me away yet. The other option is to try to tinker around the edges of established jurisdictions themselves. And here, the best success that's happened so far happened about 18 months ago in Montana, in the US, where the state legislature passed legislation that allows people to access any drug that has been that has got through phase 1 of clinical trials. So that's the time when you test for safety without testing for efficacy. And there are unbelievable numbers of drugs that get through phase 1 but do not progress through all the way to regulatory approval. Plus, even if they do get through to regulatory approval, it takes a very long time. So this very greatly expands the universe of things that can be accessed. Of course, you need a prescription, but that's not so hard to get. Prior to this, you could only get such drugs if you were terminally ill. In other words, if you had exhausted all possibilities available to you among drugs that had gone all the way through the regulatory process. So this is huge. It was largely spearheaded by an organization that I seed funded a couple of years ago called the Alliance for Longevity Initiatives. The Alliance is doing lots of other things, wants to, of course, promote the passing of equivalent legislation in other states, but also at the federal level. And certainly there's half a dozen senators or representatives that are on board with this and have formed what's called a longevity caucus. So, there's lots going on in that area. But again, I think it would be dangerous to be over-optimistic about how rapidly that's going to translate into access or into what we need, into an actual war on aging.
We had Niklas Ansinger actually from Prospera on an episode.
Oh, great! Yeah.
Yeah.
So, Niklas is a real hero. He is very strongly a part of the longevity mission, and very much has his head screwed on. He is one of the principal people at Prospera, though not one of the actual owners. And he's doing everything he can to make Prospera survive. But I have it from his mouth that if the election in November doesn't go according to plan, then they've basically got no chance.
What are your hopes for the new administration in the US?
Well, I basically agree with everybody that we have no idea. That it's an extremely, the one thing we do know is it's going to be unpredictable. But of course, in some ways, that's good. A lot of the problems that we face in any pioneering technology, and certainly in the longevity crusade, is inertia arising from basically the people at the top not having the political will or inclination to overcome the vested interests that exist trying to preserve the status quo. And we may very well see people like Donald Trump and Elon Musk and so on just, not being as we have seen in the past in that regard. So, it could be that we end up 4 years from now feeling that, a lot of absolute chaos and, has happened that's bad, but some of the chaos may be good. That's the best we can say right now.
I mean, it creates perhaps some openings that wouldn't otherwise exist. And we have, of course, we all vitalists here, and we hope to influence decision makers to make some real investments.
Right.
Yeah, so you mentioned Prospera, and that got me thinking about Bryan Johnson, who, of course, went there to get his follistatin gene therapy. He's talking about how he's outsourcing his life to an algorithm. So anything that he does should be in the direction of not dying, which sounds great. But how would you write Bryan Johnson's algorithm if you could write it for him?
Yeah, good question. So, I mean, let me emphasize first of all that I regard Bryan Johnson as unequivocally a net positive for the movement. And the large part of why I think that is because he is so utterly fearless when it comes to going out there and allowing people to laugh at him if they want to. He tells the world exactly what he's doing and why. And a lot of people think that's a crazy way to live. I personally do think it's a crazy way to live. I think it's the idea of living according to an algorithm is not really living as far as I'm concerned. But that's not the way he thinks, and he's entitled to think the way he thinks. What I believe he's offering is inspiration to the world to follow one's actual instincts, and to not just kind of follow an irrational path of a contradictory path of saying you want something or thinking you want something, but then not doing anything to make it happen. Most people don't want to die. Most people don't want to get sick, but they don't do much about it, whereas Bryan is doing as much as he can about it. As regards whether my algorithm will be different, well, yes, it would be, because I would put 3/4 of my $2 million a year that he's spending into research. I would recognize that however much I do with what can be done today, even if I have, an MRI machine in my house and things like that, I'm only going to extend my own healthy lifespan or total lifespan by a very modest amount. And the only way I'm going to transcend that glass ceiling is by taking advantage of advances that happen in the meantime, which means that my rational approach is to actually, hasten those advances so that as much advance happens in time for me as possible. And Bryan's not doing that. I'm by no means the only person who has taken him to task on this. Mark has certainly done so as well, coming back to Mark Hamalainen. And honestly, he's got no answer. So my take is that actually, in this respect, he is just like everybody else. He knows he's being irrational, but he can't help himself.
Yeah, it's going to be interesting to follow if we see some kind of evolution there. Aubrey, what are you most excited about now that we might not have touched upon? We have touched upon a lot of things here, but anything that comes to mind?
Honestly, that's a much easier question for me to answer than it used to be 5 or 10 years ago. I used to say, well, I can't really tell you because there's so many things going on. This is a divide and conquer approach. I'm excited about all these, fine details of what's going on in the lab that it would take me half an hour to just explain the background to. Now, it's easy for me to answer the question. I'm excited about getting to RMR. I think that we are genuinely within close striking distance of achieving this threshold of a year of postponement of mouse lifespan. I'm absolutely certain that once that is achieved, my job is done. There will be a war on aging basically a week later, and I will have achieved what I set out to achieve.
Are there any more math problems you can solve when your job is done?
Yeah, I work on things occasionally.
Yeah. So we've been going on for almost 2 hours now, but we've been starting to asking our guests if they can recommend 3 books. Do you have 3 books on the top of your head that you wanted to recommend? Outside of Ending Aging, of course. Ending Aging is Aubrey's book that everyone should read.
Yeah, so I'm pleased to say that Ending Aging has stood the test of time. Certainly there's been a huge amount of advances in the intervening 15 years or whatever it is, 17 years. But that's all been the kind of advances that I was predicting. In other words, we haven't had to rethink or abandon or add to the list of 7 categories of aging, categories of damage. In contrast to the Hallmarks papers, which are basically not so much a classification of damage as a classification of the literature. Of course, what we have got is a lot more technology that could be applied. So for every single one of those 7 categories, there are now multiple viable approaches to developing how to repair the type of damage, whereas there was really only one for each case back then. You didn't have partial reprogramming, for example. So that's good. Other books, well, there's quite a few. I mean, as you know, most of my colleagues have come out, many of my colleagues have come out and published general audience books on this topic over the past few years. One thing I enjoy doing is making fun of David Sinclair for the fact that it took him 11 years longer than me to write such a book. But I always point out that this is not because he's more of a coward than me. It's because if he had written a book called, like, Why We Age and Why We Don't Have to, when I did, he would have been fired. He had the misfortune to be a professor at Harvard, which I didn't have. And so, he had to worry about peer review and things like that. So now, yes, I mean, One book that I would certainly recommend is something called Methuselah's Zoo, written by an absolutely outstanding gerontologist named Steve Oerstad. A large part of why it's useful is because he is a zoologist. He understands other species, unusual species, a lot better than almost every other gerontologist, and therefore he can talk about the evolutionary, the evolution of aging and so on much better and give a better perspective. That's certainly a very important one. Yeah, and there are various others. So, Replacing Aging, which you mentioned, by Jean Hébert, excellent book. Gives highlights a bunch of aspects of how we might go about rejuvenation that are not highlighted by anybody else, certainly not in general audience form. So, yeah, that's another book I would recommend.
Perfect, Aubrey. Thank you so much for taking the time to talk with us today.
Absolutely. My pleasure. Thank you for having me.
Yeah, until next time.